As a supplemental lecture, I want to tell you about Abel's theorem and a very cool technique called summation by parts. So let's start this by pondering about a certain question, general question. So we had theorems about power series that concerned what happened inside the domain of convergence. And we also discussed a little bit that outside this domain of convergence, we expect divergence, or these have to diverge. The question is, what could happen at the boundary of the domain of convergence? So what happens when we are centered at x0, we have our x0 plus r, and x0 plus minus r. What happens at these points? And there are two things. I mean, this is an equality between two concepts. We could ask what happens to the function, but also we can just look at this series. We can see whether or not it converges at the endpoint. And there are three possibilities for power series that actually happen. And for general series, you could have other possibilities as well, but for these series, you only have three possibilities. You could have that the left-hand side is not defined or blows up. And this happens for the familiar example, fx equals 1 minus x, which is equal to the sum of x to the n. So in this case, our radius of convergence is 1. Our x0 is equal to 0. So we're interested in the interval minus 1 to 1. And if we plug in the endpoint, x equals 1, f of 1 does not exist. It's not defined. And also, the series does not converge. So if we look at what happens on the right-hand side, we get sum of 1, which would be equal to infinity. So the right-hand side diverges, left-hand side is not defined. Now, there's another two possibilities. You could have the left-hand side defined, but the series doesn't converge at limit point. So this could happen when we look at the other extreme of the same function, namely minus 1. In this case, if we look at the left-hand side, then f of minus 1 equals 1 minus minus 1 is 1/2. That's perfectly well defined, but the other side is not defined because it does not converge. So something happens here that the thing that exists doesn't equal to the other side because it does not exist. And finally, a third possibility that can happen is that both are defined. So left-hand side is defined and right-hand side is defined. So one example is fx equals 1 sum of x to the n 1 over n plus 1. And you can, if you express this as an integral of a certain function, so if you express this as an integral of a certain function, then what you get after you have to justify this step by uniform convergence, you get minus ln 1 minus x minus x. This can all be justified as long as you stay within the interval minus 1, 1. But what we get then is two expressions. Okay, well, first we get that f minus 1 you can evaluate for this function as minus ln 2 minus ln 2. And also, you can take the series expression here. So left-hand side gives you minus ln 2 plus 2. And the right-hand side, the series, if you plug in minus 1, it gives you something that, again, converges by the alternating series test. So we get two things. Both of these exist in this case. But what we have to worry about now is whether these expressions all are defined. So, so the left-hand side and the right-hand side are defined, but do we know that they are equal? So in this case, we know that the equality holds on the open interval minus 1, 1. And this calculation here in red, it requires uniform convergence on at least parts of the space. And it's true on the open interval minus 1, 1. But here we get two different values at the endpoint minus 1. So if both sides exist, do they have to be equal to the same? And this is, by the way, a Finnish painting here that I'm using by a famous Finnish painter, Akseli Gallen-Gallela. And that is Jan Sibelius, famous composer. Painting is called Problem. In this case, the problem is, when both sides are defined, do they have to equal? And in our case, can we say that these two things are the same? Well, fortunately, the answer is yes. But how does the argument has to go? Well, let's look at the structure of things. We have two expressions, left-hand side, right-hand side. They define functions on minus 1, 1. And we also have that their endpoint values is defined. Well, how can we conclude that g minus 1 is equal to f minus 1? Well, we need continuity of the functions. If they are also continuous, then from the fact that they agree on the interior, we can conclude that f of minus 1 is equal to g of minus 1. So the crucial thing here that we would need is some sort of continuity for these expressions. Well, f for us, since we have a formula for it, the left-hand side, is continuous, just like in this case. So the continuity of the left-hand side is not an issue, but the continuity of the right-hand side, which for us is a power series, is the question. And this is what Abel's theorem addresses. Abel's theorem tells us that if you have a power series with positive radius of convergence and not infinity, otherwise there is no endpoint of its infinity, and if we have that the series converges at one of its endpoints, and the series converges for independent reasons, just like from the alternating series test, then we can conclude that the function is actually continuous, including that endpoint. So whereas the theorem that we presented in class gives us continuity on the open interval, this theorem allows us to extend the continuity. So as a consequence, by the argument that we gave above, we get the formula that sum of 1 over n plus 1 minus 1 to the n plus 1 is equal to 2 minus ln 2. This kind of arguments you've used in calculus, actually, but you have not justified them properly. And actually, they're quite difficult to justify. So it's interesting, partly because it justifies such summation formulas. But okay, we need a tool for this. And the tool is called summation by parts. It's a way of changing a sum into a different form. So let's recall the partial sums of an, s, and s capital N. And then and for notational reasons, let's define s minus 1 to be equal to 0. So sum from 0 to capital N, an, bn. Now an is the difference of two terms, Sn and Sn minus 1. And this we can now split to two different parts. So we have Sn bn plus, with a minus sign, Sn minus 1 bn. Now these are grouped with the bn term, but we want to group with the Sn minus 1 term. So we want to shift the index from the other term to be n. We have minus, n goes from minus 1 to n minus 1, because if n goes from 0 to n, n minus 1 goes from minus 1 to capital N minus 1. Sn bn plus 1. And then we examine these terms. First of all, terms that are included in both of these are terms from n equals 0 to capital N, Sn bn, n minus 1. And then we have an extra term here, Sn, that was the Sn minus 1 term, but we had set that equal to 0. And additional to that, we have the capital N term here that is not contained in the second sum. So we have S capital N, B capital N. On a second look, it's nice to draw an analogy between this and another formula that you've seen, namely integration by parts. And this is where the name, this technique, comes from, summation by parts. The analog of summation is integration. So let's look at this expression here. We could think of this summation of the product as being the integral of a product. And let's put an f prime here. Here we have a difference, and this difference here is the analog of having f prime. So really this is an integral f prime times g. And then what do we get here after these steps? Well, we have integral of f g prime with a negative sign, and then we have a boundary term, fg.
Summation by parts is a surprisingly useful tool, especially in settings where you can control the sums of expressions. Now we'll see how that applies to proving Abel's theorem. Let's fix some things in our proof. So we are considering a power series that we know converges on the half open interval up to -1. And we can normalize the center, x0 to be 0, and the radius to be 1. This is obtained by translating and scaling the variables in such a way that our radius of convergence is actually equal to 1. Now the claim is that it's continuous on the whole interval where it is defined. So the first part is easy, namely the interior of that set, -1, 1. And in that case, we know that the function restricted to that open interval is continuous by the theorem about convergence of power series. So the next thing, what we really want to prove, and the heart of this proof, is proving continuity at 1. And pictorially what is happening, what we want to prove is that if we take an x and send it towards 1, that the value of the function f of x converges to the value of f of 1. Well, we'll need to make some choices, epsilon and n. But before we know what choices to make, as usual, we'll have to estimate. And we'll want to estimate fx minus f1. Well, f1, we know what it is. It is the infinite sum of an's. Now the trick in this proof is to write f of x in a different way. And this is where we apply summation by parts. The reason for this is that we want to change the an's into sums of an's so that we can compare them to the right-hand side here. So how does it work? Well, we have to first talk about partial sums before we can take an infinite sum. So let's sum up to m, a and x to the n. By summation by parts, if we take partial sums of these terms, so Sn of is equal to sum from n equals 0 to n, or k equals 0 to n of ak, and s minus 1 by convention is 0, then the sum of a and x to the n is the same thing as sum of Sn minus 1 x to the n. And by the regrouping of these terms, by grouping instead by Sn's, well, every Sn multiplies x to the n, and that's these terms, but it also multiplies the consecutive one, because n minus 1 multiplies the n term with a negative sign. So when we re-index, we get Sn x to the n plus 1 with a negative sign. But there's one term that doesn't get counted in this summation, namely Sm x to the n. The single term that is not included is when the index here is equal to m, and that gives us one extra term. The other term, s minus 1, which is counted in here, will give us 0 because we have that sum is equal to 0 by convention. So we have this formula. Now let's write this in a little bit different way. So from here, we can take a factor out, 1 of x to the n, and then we're left with Sn x to the n. And then the other term, Sn x to the n. Now, the next thing we want to do is we want to send m off to infinity, because we want to get a function expression on for the function f. And we do this on the open interval 0, 1. So here x, without loss of generality, is in the open interval minus 1, 1, because when it's equal to 1, there's nothing to prove. So with that in mind, we send m off to infinity, and I'll do this in one line. So left-hand side here converges to f of x by assumption. So this gives a formula for f of x that will be useful. And the right-hand side, this term here converges to the infinite sum. Well, let's be a little bit slower. We don't know that this series converges. But how can we conclude that it converges? Well, this left-hand side converges. This thing converges. We'll soon say to what. So if we move this term on the other side, we also get that this converges. And what does it mean for that to converge? It means that in this case that the series from n equals 1 to infinity of Sn x to the n converges. And this summation, by the way, should be from 0. But what happens to this other term? Well, x is in minus 1, 1. Sm is convergent. So this has an absolute value bounded by some m because it's convergent. Let's call it L for all m because it's converging. And x to the m is going to 0. So by that, we actually get plus 0, but I don't write that here. So we get a new formula for f of x, which is somewhat surprising. 1 minus x times a product. The nice thing about this is that 1 minus x is going to 0 and x is going to 1. And the second term here, we'll control in a different way. Okay, so let's write this expression that we got here for f of x. And this is valid only on minus 1, 1. Now, we do a common trick that we split this expression into small terms and large terms. So we split this term, the small and large terms. Well, we'll do the splitting, but before that, now we'll do a trick of writing. This is a constant here. We'll write it a little bit differently. So let's call this S infinity. It's the infinite sum. Well, we have 1 minus x, sum n equals 0, infinity, Sn x to the n. But S infinity, it can be written in a funny way. 1 minus x times 1 minus x. And this can be written as a series, 1 minus x times the sum of x to the n. Now, why we do that is if we pull with a factor of S infinity here, if we pull that together, let's do it in 2 steps to make it more visible. And what we have here is S infinity x to the n. Now, these 2 summations look very similar, so we can combine the terms to each other. Sn minus S infinity x to the n. Now we're in a good setting because these 1 minus x is going to 0 when x is going to 1. And when n is large, this term is small. So let's do 2 estimates. We'll split this sum first into small terms and big terms. So 1 minus x, sum n equals 0 to some capital N, which we have yet to choose. And then terms that are big. One minus x, sum n equals 0, n equals capital N, infinity, xn, Sn minus S infinity. Okay, well, these are estimated. They will both be less than epsilon over 2 and epsilon over 2, but let's see the bounds for both of them. So for the first one, what we will use is that this has a factor of 1 minus x times, if we estimate the sum from above, each of these terms we can bound by 2L, because Sn, recall, was bounded by L. And S infinity, because it's the limit of Sn, will also be bounded by L. And the x to the n we can bound by 1, because x is in 0, 1. So we get a bound of this whole expression by this, but this is a factor of 1 minus x. So if we make delta sufficiently small, so if delta is less than epsilon over sum n equals 0 to n 2L and 2 times this, then we get this term. This will depend on the choice of that. Now let's look at the second term. We bound that from above as well, but we will bound that in a different way. So this is bounded from above by absolute value of 1 minus x. Well, that's positive, so 1 minus x times, we pull the absolute values inside the sum. Well, when we do that, we get x to the n times absolute value of Sn minus S infinity. But this expression here, once n is large, this is less than epsilon, so this is less than epsilon, 1 minus x, sum, this geometric sum here, which is equal to x to the capital N divided by 1 minus x. And this whole is now less than epsilon, because x is in 0, 1. Minus 1, 1. have absolute values. Well, x is close to 1, so no x. So if we choose epsilon 2 here, then we're good. Okay, so how do we get these choices? Well, here we use convergence of Sn, and here we use boundedness of the sequence, two different ways. So let's do these. We'll fix L such that sum n equals 0 to capital N, an is all bounded by L for all n. Let's use a different index, Sn, and sum ak. And therefore also S infinity will be, because it's the limit of them, is less than or equal to L. Then let's fix an epsilon. And we will choose n so that for n bigger than or equal to n, Sn minus S infinity will be less than or equal to epsilon over 2. With that fixed, we will finally fix our delta to be equal, less than or equal to, how small did we need? We needed it here in this term. So in this we can simplify by epsilon over 4 n plus 1 L. So if we fix it, delta positive epsilon over 4 n plus n, n plus 1 L, then everything here works. Well, this calculation didn't depend on any choices. And once we have an index bigger than, well, we don't need any m here. Once we are x is close enough, well, these were inequalities. This was triangle inequality. And this red term here is valid because delta is indeed less than that. And this blue term here will be less than epsilon over 2 because our indices in the second summation are big enough. This gives epsilon over 2, and then as a sum, our desired epsilon, and completing our object. So this is a complex proof with many estimates. Now I want to highlight two things at the end. One was the trick of summation by parts. This plays a crucial role in this proof. And the second was this splitting. Once we had applied it here, we split the sum that we got. There was another trick here in between that we expressed this as a sum. We split it into small terms and large terms. And for large terms, we applied one bound. And for the small terms, we applied another bound. In doing these bounds, we encountered this issue that we had to choose things, and we had to choose them in order. Here, we got a capital N, and then based on that choice, we chose delta. This order of choosing first an n and then a delta is pretty common. It occurs a lot in sequences and series. But with those bounds, with those choices, we got our proof.